Well, thank you for the introduction. Today I want to tell you about some of our research in the heavy element chemistry program at Lawrence Berkeley National Laboratory, where I'm currently a staff scientist. My research involves a lot of synthetic chemistry, but also leverages some of the really unique experimental facilities we have at LANL, including things like the Advanced Light Source. We also use synchrotrons around the US and abroad. All of my research, though, is really fundamentally focused on looking at F orbital interactions in lanthanide and especially actinide systems, and trying to understand how those F orbital interactions actually determine physical properties. And we're interested in properties as basic as things like magnetic behavior to bond lengths and solubility. And as a chemist, one of the things that I'm most interested in trying to understand is whether or not we can actually control those F orbital interactions and then tune them using ligand designs to get out better physical properties. And whether or not you can actually control actinide behavior using different ligands is something that's been kind of an open question for a pretty long time. And I think you can trace that back to some of the early days with Glenn Seaborg. So Glenn Seaborg and coworkers have what's become sort of a classic paper in actinide chemistry now, which is really the first where they proposed that there might be some potential for covalent bonding in the actinide elements. Now, despite having proposed this quite a long time ago, debates about the amount of actinide covalency have really persisted throughout the last century or so. And one of the challenges is that a lot of the kinds of language that we would use to describe actinide covalency, or to describe covalency in things like transition metal systems can be really hard to employ for actinides. So things like molecular orbital theory. Now, most of the original arguments in favor of covalency, so a lot of the argument that was proposed by Seaborg and coworkers was focused mainly on the greater radial extension of the 5F orbitals and how that would be larger than the radial extension of the 4F orbitals observed for lanthanides. And so you can see here that the 5F go out, there's some density out here, even above about 1.5 angstroms, and so if you have a ligand that could get close enough, there's the potential for some productive overlap that could lead to covalent bonding. Now, still, even since the 1950s, most aspects of actinide chemistry have been best described using ionic models. So you really don't need to invoke covalent bonding to explain solubility, bond energies, bond lengths, etc. You can usually use size to charge ratios or things like oxidation states. Now, one of the challenges associated with using things like molecular orbital theory to talk about actinide bonding stems from the large number of orbitals that can be involved in a chemical bond. So we don't just have d orbitals, we also have the f orbitals. And actually there's additional orbitals that can get involved. So the 7s, the 7p, there are also pseudocore orbitals, the 6p, that can get involved. And sometimes all of these orbitals will hybridize in low symmetry systems, which can really make things pretty messy. And I'm showing here, obviously not all the d orbitals. There's 3 here. And then here, there's not all 7 of the f orbitals. There are 2 more that you can obtain just by rotating 90 degrees on the z-axis. There are also relativistic contributions to electronic structure that can't be ignored. And I haven't even talked about any of the radiological issues associated with doing experimental work on actinide systems, which can really make things pretty challenging. Now, one of the most prototypical examples of actinide covalency historically has been the actineals. And I'm showing here 3 examples of actineals. So this is uranyl tetrachloride, and then we have the neptunium and plutonyl tetrachloride systems. I chose the tetrachlorides because these are commonly studied analytes for spectroscopic purposes. And you might have noticed that I've also chosen to draw 3 lines here between the metal center and the oxygen ligands. And this, some people choose to draw 2 lines, some people do 2.5 lines. I choose 3 lines because there's essentially 3 d orbitals that can engage in metal oxygen bonding and 3 different f orbitals that can engage in metal oxygen bonding. And if those are all occupied, then you have the potential for these 3, a triple bond here. And that's partially also why we do this partial positive charge on the oxygen atoms. Now, a lot of the question about whether or not these are very covalent systems, or one of the questions that this raises is, why are these potentially so covalent? Is it simply a symmetry effect? Because in this system, you can't have mixing between the f and the d orbitals. Or is it because the 5f orbitals are a lot lower in energy? You have here a highly oxidized metal center with a lot of charge, so maybe that's pulling those metal orbitals closer in energy to the ligand-based orbitals. Some people might dispute that these are very covalent systems anyway. There's a lot of different reactivity or other experimental data to suggest that they're not really all that covalent. And one of the big questions is, how does the nature of the covalency change as you move across from uranium to neptunium, plutonium? You know, I've drawn 3 lines in each of these instances, so that doesn't tell us very much about the nuance as you move from one metal to the next. Fortunately, I think that the actinide community has somewhat settled on a very basic description of actinide bonding in recent years. And this has to do with our understanding of how the d and the f orbitals change from one metal to the next. And so what we know is that the d orbitals essentially stay at the same energy or perhaps increase very slightly. But the 5f orbitals, because these have more density at the nucleus, actually drop off more significantly. And so if you think about a simple MO diagram like the one here on the left, where you have an interaction between 2 atomic orbitals, you can imagine that as these orbitals here were dropping in energy, that would give you a smaller energy gap here between a metal and a ligand. And if we think about it, it's just a simple equation for the orbital mixing coefficient, which I've shown here as lambda. An increase or a decreasing energy gap here would result in a smaller denominator and an enhancement in the orbital mixing. And so this basic sort of concept has been used to describe a lot of trends in actinide covalency in recent years. The problem with it is that it doesn't require invoking orbital overlap. And what we know from perturbation theory is the actual energetic stabilization of a bond is proportional to the overlap squared. And so you can potentially have systems in actinide molecules where you have a large amount of orbital mixing because this energy gap is very small, but actually very little energetic stabilization or very little perturbation of the f orbital manifold because there's very little overlap. And so a lot of the goal of my chemistry recently has been to try to design experiments that allow us to really specifically probe and quantitatively probe this role of overlap in actinide molecules, and hopefully to have selectivity so that we can look at the various different sigma or pi components in multiple bonding interactions. The technique that we have been using is commonly referred to as Ligand-K X-ray absorption spectroscopy. This is sort of an umbrella term which is used to talk about any form of K-edge spectroscopy where you're looking at transitions based on the ligand. I know that many people in the audience here are very familiar with this technique, so I'm not going to go into a ton of detail here. I'm just showing a simple K-edge spectrum. In this case, it's the chlorine K-edge for titanium hexachloride, a nice D0 octahedral molecule. What we're looking at are the intensity of these pre-edge transitions at low energy. And these are associated with excitations from the ligand 1s, in this case a chloride, into antibonding molecular orbitals that are formed by mixing between the chlorine 3p and the metal D. In the case of an actinide, it would be f orbitals. And the intensity of these transitions is directly related to the amount of chlorine 3p character in that, that sort of hybrid orbital. And so we can use the intensity there to back out the mixing coefficient, which I've shown here, again, is lambda. Now, this technique has been around for quite a long time. Ed Solomon and coworkers at Stanford really, I think, pioneered using this technique as a quantitative measure of metal-ligand covalency in inorganic coordination compounds. And so we've adopted a lot of their methodology in our work. I've highlighted here some advantages, I think, of using Ligand-K XAS. One is that you're probing the covalent nature of the bond really directly. You're not having to infer it based on another observation. If you do the measurements well, it can be quantitative and give you experimental orbital mixing values. It also gives you a really nice, pretty feature-rich spectra. And so if you're collaborating with theorists, this can give them a lot of data points to evaluate whether their calculations are doing a good job of matching the spectra. And also the results are directly comparable with MO theory, which is a language that's familiar to many chemists. Now, for many years, a lot of the work we were doing initially was at the chlorine K-edge or at other higher energy K-edges like sulfur. But in the last 10 years or so, we've gotten more interested in trying to look at some of the lower Z elements like carbon, oxygen, nitrogen, and so on. And in order to do those measurements, we took advantage of another more recent innovation in synchrotron instrumentation. That's the scanning and transmission X-ray microscope, or STXM. And we have access to a few of those. I'm showing here a picture of the one on beamline 1102 at the advanced light source. And this technique is really advantageous for quantitative studies because it allows you to take measurements in transmission mode from very small, very thin particles. And so you can avoid a lot of the problems with things like self-absorption or saturation that you might encounter using more traditional detection methods. We have a pretty broad energy range. I don't know that we've gotten down to 100 eV recently. Probably 200 is more realistic, but it normally includes down to around the boron K-edge up to the silicon K-edge. We can obtain spectra sometimes as fast as just a few minutes for a coarse spectrum, and occasionally we might take something as long as an hour if we need more detailed data. It can provide very accurate results. So spatially, we have typically around 40 nanometer spatial resolution, depending on which zone plate we're using. And our energy resolution at high energy, so at like the aluminum K-edge, might be somewhere around 0.2 to 0.4 eV. But if you go down to lower energy, like at the carbon K-edge, it's closer to 0.1 eV. What's really advantageous for our work actually comes from how you prepare the samples. So we use these aluminum plates, and at the end mount these little silicon nitride supports. We'll typically apply our sample either by brushing particles as a small powder, a fine powder, and so you can see a particle here, or by depositing a solution to get crystals to form on the substrate itself. And then after that, we'll attach a second window and seal all those edges up with epoxy. And so this provides a really nice barrier to the air and also some containment for radioactive samples. So as I said, we do a lot of these measurements historically at the ALS. More recently, we've been also doing a lot of work at the Canadian light source, which has a very similar STXM. This is a picture of some of us at the STXM at the Canadian light source just prior to the COVID lockdown. Normally we don't travel with this many people, but this was a really good opportunity to train some new users. Here, this is Jacob Branson, and he's done a lot of the experimental work I'm going to tell you about today. Alex Ditter is another postdoc working with us, and David Shu, and he's been enormously helpful throughout a lot of these measurements. Another postdoc here, Yusin, and then Professor Taoxing Sun, who's been visiting us, or was visiting us just prior to COVID, participated in many of these measurements. Oh, and I just wanted to briefly highlight that in terms of sample preparation here at LBNL, we have access to a lot of synthetic facilities for doing and for sample preparation. One of the things that we're most excited about actually are these new inert atmosphere negative pressure glove boxes. And so this allows us to make samples that are potentially organometallic and might be air sensitive. And so we can get into some types of spectroscopy that we haven't really been able to do in the past. This is just sort of a montage of a lot of the different types of analytes that we've looked at over the years. For today, I'm only going to focus on a couple. So there's the actinyl tetrachlorides, which I've already introduced to you. And then in the second part of my talk, I'll talk about these actinide hexafluorides. Before I do that, though, I just want to take a couple more minutes and mention some of the work that we've done on these organometallics. This is going to be a bit more of a technical discussion that I thought might be of interest to this audience regarding the potential for radiation damage when doing spectromicroscopy. So obviously the way that STXM works, we use a zone plate to focus the beam down to a small point and take data from very small particles. And so anytime you're focusing that much flux on a small area, you have the potential for radiation damage. In my experience with our samples, this typically takes the form of damage either to samples that have some component of liquid in them, or if they have highly oxidized metal atoms. Otherwise, we usually don't encounter any problems with radiation damage. On this slide, what I'm showing you are some images of organometallic that we deposited from a toluene solution, and the sample wasn't properly dried. And so there's probably a lot of toluene that was still entrained in the crystal lattice. And after scanning, what you could see is that there were a lot of these sort of disruptions in the crystal, which we attributed to the toluene essentially boiling off and then fracturing the crystal as it tried to escape. Now, most of the time we are able to avoid this kind of thing by just drying our samples properly. And usually our samples are solids. Occasionally we do look at some liquid samples, but that's a bit more rare. For liquid samples, you can mitigate some of these potential problems with low temperature measurements, and there is a cryo-STXM available, the Canadian light source, which we've used in the past. But most of our issues have to do with redox sensitivity. And in that case, we reduce radiation damage by just limiting the exposure time. And I want to show an example here of how this works. This was organometallic sericine. So this is a cerium-4, a high valent cerium center. And it's very susceptible to photoreduction in the beam. And we can observe that both at the carbon K edge or at the cerium M5 edge. And so what this slide shows is that if you look after repeated scans, the spectra in blue begin to disappear and the spectra in red begin to emerge. Now, what's nice is that we can actually characterize the radiation damage in this case, and so we're able to control it. In this case, by reducing the photon flux, reducing the dwell time for each data point, minimizing scan durations overall, taking a smaller energy range, and then averaging many data sets. And so for sericine, even though this was a very highly sensitive compound, we were able to ultimately get very good quality spectra. And we have been able to also get data from other very photosensitive compounds, things like permanganate, which are well-known light-sensitive compounds. Another way that we help avoid radiation damage is by how we prepare our samples. So using this solution deposition method, we're able to arrange a large number of very thin particles in a small area. And so instead of having to get data out of a very small particle, we can typically spread out our dose over a larger area and still be within the sort of linear regime of the Beer-Lambert law. All right, so that, I think I'm gonna pause here and see if there are any questions before I move on and talk about the work we've done on the actinides.
Great. Thanks. Are there any questions, anyone? You gave a very nice introduction and motivation for the work. I guess I might have chemistry questions, but I think I'll wait until later when you talk about these.
I have a question.
Sure, he has a question.
Okay. STXM is tremendous, and of course the optics, the phase plates help make that possible. How much of what you're learning with STXM with soft X-rays is going to end up, do you think, being helpful for the growth of nanozanes, of course, called something different with hard X-rays?
Unfortunately, I'm not familiar with that technique. Is this like what energy range does nanozanes typically work at?
Ordinary hard X-ray energies with the higher brilliance of the various upgraded synchrotrons. People are getting down to 30 nanometer spots and doing scanning and whatnot.
Oh, okay.
So I think very similar issues are probably going to come up. You know, the penetration depths are different, but anyway, I was just curious if you had any thoughts. I apologize for the interruption.
No, I mean, I can tell you that we have done some higher energy measurements. So working at the carbon K edge is very different from working at the silicon K edge, for example. So to get transmission at the carbon K edge, you have to have a sample that's less than 100 nanometers thick at least. But when you get up to the silicon K edge, sometimes you want to have samples that are several microns thick at least in order to get enough signal. One of the disadvantages of working at such a low energy is that you have to have the optics right up next to the sample. And so this really limits the kinds of sample environments that you can have. But when you go to higher energy, you can accommodate things like solution cells. You can do in situ electrochemistry. And so I can imagine that this hard X-ray technique would really open the door to all kinds of more exciting techniques that we can't really do with these very soft energies.
Okay, thank you.
Good. Okay, so let's go on. And if you have, for everyone else, if there are more questions, just put them in the chat or say you have a question. I'll call on you the next round. Okay, go ahead.
Okay. Well, so I want to begin with a little bit of background on the actinyls. I already showed a slide on these earlier in my talk, but a lot of our understanding of actinyl chemistry comes from some earlier oxygen K edge work that was done by Bob Denning and Jenny Green. And here they used a single crystal of dicesium uranyl tetrachloride, and were able to do a polarization dependent study and show how the different transitions that they observed at the oxygen K edge could be turned off or turned on depending on the orientation of the crystal relative to this beam. And it was in this context that they proposed a really important aspect of the electronic structure in actinyls that's known as the inverse trans influence. So this is sort of opposite to the normal trans influence that you would see with transition metals, where bonding trans to a strong field ligand actually acts to enhance mixing in that transposition. And this is due to hybridization of the 5F and the 6B pseudocore. And so initially when we set out to do this work, we wanted to see if we could just reproduce this sort of polarization phenomenon that they observed using STXM, and then to see if we could actually get quantitative data for our measurements. So these are the systems I'm going to talk about. I'll begin just by telling you about a system with no oxygen ligands. This is uranium hexachloride. We'll pluck off one of these chlorides and replace it with an oxo to get uranium monoxo pentachloride, and then replace the trans chloride with another oxygen to get uranyl tetrachloride, and then move to neptunium and plutonyl tetrachloride. Just to orient everybody to the electronic structure that we would expect here. So these are this is the molecular orbitals for simple octahedral uranium hexachloride. We have the EG and T2G that we would expect for the d orbitals, and then here are the f orbitals in octahedral symmetry, which split into T1U and T2U sets, and then the non-bonding A2U set. Now, if we replace one of those chlorides with an oxo, what happens is that we're going to split these orbitals and destabilize the ones that are involved in bonding with the oxygen ligand. And so I've highlighted those orbitals here in red. And then if we replace an additional chloride with another oxo, we'll further destabilize those orbitals again. One thing you might notice is that this orbital of A1 symmetry really goes up in energy when you go from uranium monoxo pentachloride to uranyl tetrachloride. And we initially thought that this, just based on the ground state DFT calculations, might be attributable to that inverse trans influence that I was describing before. Oh, and these are just some cone-sham plots of those orbitals, but let's talk about those. So here on this slide, I'm showing the Ligand-K X spectra that we obtained. Obviously, I don't have uranium hexachloride, but here's uranium monoxo pentachloride and then uranyl tetrachloride. The only difference between our data on the uranyl tetrachloride is that we have tetraphenylphosphonium countercations, so it's a cesium. And our data was obtained using elliptically polarized light. And with this particular crystal, the actinial axes aren't aligned, and so we think that our data is really average, showing an average sense of the bonding across the actinide oxygen bonds. But we still see the same sort of overall peak pattern, a spectral profile that was observed by Denning and Green, and we can adopt their assignments, first peak into or transition into the EU, then the A2U, and then here the EG. Now for uranium monoxo pentachloride, this hadn't been reported previously, and we would expect potentially up to 4 transitions, and using our simple Gaussian curve fit, we see 4 peaks. But when we looked at the DFT calculations, it was a little unclear. So the initial DFT calculations agreed quite nicely for uranyl tetrachloride, but for the uranium monoxo pentachloride, here at low energy, there was not a great match. And this gave us a little bit of concern about our assignments. And actually, we've had this experimental data for quite a while, but haven't published it yet because we were still feeling unsure about the assignments. It was more recently that a postdoc working at Los Alamos with Ping Yang and Enrique Batista, so this is Joe Casper, he did a deep dive into the calculations and found that you actually have to incorporate spin-orbit coupling in order to get a good simulation of the data for uranium monoxo pentachloride. It's not necessary to include spin-orbit coupling for uranyl tetrachloride, but it is for the monoxo pentachloride, even though these are both formally F0, D0 systems. It's not entirely clear to me why this is the case, but you get a much better simulation this way. And then using those calculations, we're able to properly assign our spectra. And what we see is that the transitions into these low energy orbitals of E symmetry are actually split between both of these functions here. And then at higher energy, it's a more straightforward assignment. We have a simple excitation into the orbitals of E symmetry. And then in this case, we actually do still see the transition into the A1. This is the 60 dz squared orbital. Now what we can do is integrate under the area, under these Gaussian peaks, and try to compare changes in covalency. I'm going to go through this kind of quickly because it's a little complicated, but basically what we observe is that the intensity under these purple features here, which is associated with the 5F sigma transitions, is about the same in both instances, but in this case, it's convoluted with some of this pi bonding orbital. And so we think that this means that there's an increase in the amount of sigma bonding in the uranyl tetrachloride system, which would be consistent with that inverse trans influence, which I described before. And we also see this reflected in just the simple change in peak energy. So you can see there's a much larger change in the energy of this transition. It's almost 2 eV, or a little over 2 eV actually, when you go from uranium monoxide pentachloride to the uranyl tetrachloride, whereas the other features change by a smaller amount. Okay, so now moving on from uranyl to neptunial and plutonyl. One of the first things that we wanted to do was to try and see if we could see the same sort of polarization dependence with neptunium and plutonium that was observed previously for the dicesium salt of uranyl tetrachloride by Denning. And so these are all STXM measurements. With STXM, we can control the polarization of our beam using the elliptically polarizing undulator. We cannot easily control the orientation of our crystals, though. And so these polarization measurements are not quite as nice as what Denning observed, but we are able to reproduce the overall phenomenon, suggesting that the trends here at least are pretty similar, or the peak assignments should be similar from one compound to the next. Now, to try and do a more quantitative study, we, instead of using cesium countercations, use tetraphenylphosphonium. Again, because this gives us an average position of the actinial axes, and then instead of using linearly polarized light, use circularly polarized radiation. This slide is basically just to show that we were able to control for any issues arising due to radiation damage by depositing our crystals from solution, and then we can actually monitor the oxidation state of the metal center using N5-4-edge X-ray absorption spectroscopy and see that the oxidation state isn't really changing. And here on this slide now we have the data. I'm sorry I reversed these. So there's uranium. This is actually plutonium, but then neptunium. What we see looking at the fit here is that when you go from uranium to neptunium and then to plutonium, we see the same overall 3-peak pattern, but the peaks are beginning to broaden and then actually split into multiple features, such that for plutonium, we really have to incorporate additional functions in order to accurately model the data. But just using these same simple assignments, we can try to evaluate changes in the amount of orbital mixing in these F orbitals of EU and then of A2U symmetry. And that's what I've tabulated here on the right. What we find is that regardless of whether we look at the intensity of these X-ray absorption transitions, or if we look at TDDFT calculations, or simply if we look at the Mulliken population analysis from DFT, we observe an increase in the amount of covalency when you go from uranium to neptunium, both in the A2U orbitals and in the EU orbitals. And then we see a slight decrease when you go from neptunium to plutonium. This was initially a little surprising because I kind of had expected it just to be a monotonic increase from uranium to neptunium and then again to plutonium, not this sort of non-monotonic trend. But I've developed a model which I think actually describes what's going on here pretty well. And so to introduce this, I'll perhaps remind people about a really nice paper. It was from a while ago now by Gus Cascaria and Richard Martin, where they did DFT calculations on the tetravalent actinide dioxides. And what they showed is that as you move across the series, the 5F orbitals are dropping in energy, and you get a near degenerate energy match with the oxygen 2p right around americium or curium. So they proposed that the covalency was maximized right around there. Now, what happens when you go from a tetravalent actinide center to a hexavalent actinide center? You're increasing the charge, and that's going to pull all of the 5F orbitals down in energy, such that we think now for the actinials, we're getting this near degenerate match a little earlier in the actinide series around neptunium or plutonium. All right. Now, what's nice about this sort of model is that it helps us understand these changes in covalency fairly easily. The problem, though, is that it necessarily does not invoke overlap. And so it's not very easy to attribute our changes in covalency measured spectroscopically or with theory to changes in the stability. And so the next thing that we've been working on has been trying to design experiments where instead of varying the metal, we're going to vary the ligand and see if we can control for changes in overlap. But before I talk about that, maybe I'll pause one more time and see if there are any questions.
Right, great. Thank you so much. Yeah, for anyone who has questions, please raise your hand, or I think Yang Ha has a question. Go ahead.
Yeah, so it's very interesting. It's really fundamental talks and reminds me my old like ligand field theory. So I'm not very familiar with the symmetry of those F orbitals, but is there any like configuration interactions among the d orbitals and the f orbitals and potentially s and p when you consider their like bonding or molecular orbitals?
Well, so in this particular system, part of why we chose this system is that it's centrosymmetric, and so the d and the f orbitals are forbidden from hybridization.
Can you move on to your MO diagrams?
Yeah.
Yeah, here, like both I see like E symmetry in the, oh, okay, you're looking at the very right. Okay.
Yeah.
And what about S and P? Is there any chance they can just configure and interact?
Yeah, so the 6p pseudocore is known, or it's been hypothesized that the 6p pseudocore is hybridizing with the 5f orbitals, and that this is what's responsible for that inverse trans influence that I mentioned. So that this actually enhances the diffuseness of the 5f and results in greater overlap.
Okay, and also another question. So if I'm understanding it correct, you're trying to figure out something like a Williams-Irving series in the like 3D transition metals. In your case, it's the F blocks, and you already realized that some like the Z effect, or effective nuclear charge, does come into play as well. So can you use the d orbitals to use that as a calibration for your effective nuclear charge, and maybe just plug that into your f orbitals to basically dissect the two terms?
Use the d orbitals.
Because I remember in one of the figures you showed that the level of the d orbitals don't change.
Yeah.
These metals still have their like Z effective or effective nuclear charge effect. So can you use the change on those like d orbitals calibration for their effective nuclear charge?
I see what you're saying. Yeah.
Go back, plug that back in to figure out what you are interested in, which is the change of the f orbital energies.
Yeah, that's an interesting idea. I hadn't thought about that, but maybe certainly you can see here that when you go from uranium to neptunium plutonium, there's not a very significant change in these transitions into the d orbitals, which is kind of what we would have expected. The d orbitals are not as sensitive to the nuclear charge, and so I'm not sure that they're going to report well, at least within the energy resolution of our measurement.
Okay.
But it's something I'll have to look at. We especially if we could compare systems where we keep the metal the same and they're just varying the ligands, like I'll tell you about in a minute.
Okay, thank you.
Great. Actually, on this plot, I had a question also. It looks like from here that there's a lot more polarization dependence or variation with the 5f sigma bonds, or maybe that's because they're A, than with the 5f pi bonds or the 6d pi bonds. Is that a feature of sigma versus pi for polarization dependence in these crystal structures? That seems unusual to me, but maybe I'm not understanding that.
I don't know that you can take these spectra that quantitatively because we can't control the orientation of the crystals themselves.
Okay.
Another issue with these samples, so in order to do the polarization dependence, you have to take the same spectrum on the same area, same crystal, multiple times. And so I didn't mention this, but there's always the risk that there's some radiation damage that occurs in the course of these measurements. So we don't treat, as part of why I put the intensity scale as arbitrary here, we don't treat these intensities as really being very accurate. I think that the trends are realistic, but this is part of why we then, for looking at changes in peak intensity, we switch to the other system with the organic countercation.
Okay, great. Thanks. Okay, so Stefan, please continue.
Yeah. How much time have I got left?
We'll go to the hour, and if you need to leak a few minutes, that's okay. So,
I think I just have a few more slides. All right. So as I was saying at the end there a moment ago, one of the things that we wanted to try to do with the next phase of our work was to try and essentially control for changes in the 5f orbital energies by keeping the metal constant. And instead, what we're going to do is vary the ligand. And we decided to look at hexahalide complexes because these can be prepared for a lot of different actinides with a lot of different halides, and they're all very isostructural. So they're great for spectroscopic studies. And we essentially had two different hypotheses here. One was that for larger halides, things like chloride or bromide or iodide, these would be more polarizable, and you would then have a better overlap with actinide systems. But another hypothesis was that you would actually need smaller halides like fluorides because they'd be able to get closer and have a better overlap with the very contracted 5f orbitals. And so we really weren't quite sure what to expect. Fortunately for us, a lot of the work had already been done looking at chloride systems. So I've included some references here. This is work done by our colleagues at Los Alamos. And so for us, we mainly have been focused on trying to do the analogous fluorine K-edge measurements. There was a bit of synthetic innovation required in order to get this work started, and I'm not going to go through this in too much detail in the interest of time. Suffice it to say that even though these are very basic molecules, we did quite a lot of work to try to make sure that our analytes were really optimized for the spectroscopic studies, in particular by having non-coordinating countercations and by eliminating sources of water, which would normally hydrogen bond with the fluorides. So taking a page from our earlier work at the chlorine K-edge, we also started with some simple transition metal systems. So these are fluorine K-edge spectra for titanium, zirconium, and hafnium. Really nice systems that only have d orbitals. And you can see for titanium, we have these two peaks, which can be very easily assigned to transitions into the EG and the T2G orbitals. When you move to zirconium and then to hafnium, the transitions into the EG begin to disappear under the white line, so we're not resolving those as effectively. We can take the intensity under these peaks. We see a small increase when you go from titanium to zirconium, and then an additional increase when you go to hafnium, which we initially have been attributing to the more diffuse d orbitals for hafnium and zirconium relative to the 3D for titanium. We've also been doing some DFT calculations, and here actually I just need to quickly acknowledge the ingenuity of Joe Casper at Los Alamos, who found an issue that we were having initially with our TD-DFT calculations, which initially agreed with our assignments, but we're not getting the relative intensity of these transitions right. And also we're predicting this additional low energy feature, which we were never observing spectroscopically. So he switched to a different computational methodology, so using X2C calculations, and then by removing effective core potentials, was able to get much better agreement with our experimental data. So I think that was interesting to point out. And we can compare our results now for the fluorine-K edge to earlier work done at the chlorine-K edge. So these are the same metals, but with chloride ligands. You see a very similar spectral profile. Again, the EG peak is beginning to disappear under the rising edge. One thing that you'll notice is that the intensity of the transitions at the fluorine-K edge is much larger than the intensity of the features at the chlorine-K edge, just simply by using this curve fitting. However, you can't directly compare these intensities because there's a significant difference in the transition dipole integral for measurements at the fluorine versus measurements at the chlorine-K edge. So this is essentially the inherent overlap between the 1s orbitals and the 2p in the case of the fluoride, or the 3p for chloride. Here are spectra that we've obtained relatively recently, actually, for the actinide hexafluorides. So this is uranium, neptunium, and then plutonium. Based on our earlier work with the transition metals, we were able to easily assign this main peak here into the d orbitals of T2G symmetry. And then what you find is that as you move across the actinide series, there's some emergence of these additional low energy features. And based on our earlier work at the chlorine-K edge, we initially attributed those to transitions into orbitals of 5f symmetry, either the T1U or the T2U orbitals. We can also integrate under those functions and get a relative sense of the change in covalency here. So for uranium, we have an intensity of 1.8. This increases to 2.1 for neptunium, and then it seems to be decreasing to about 1.7 for plutonium. I want to point out this is very preliminary data, so we haven't had a chance to reproduce the data for plutonium yet. So we'll want to confirm that this is a real value before publishing it. But using an intensity standard that we've developed for the actinide hexachlorides, and then more recently for the hexafluorides, we can relate these intensities to experimental values for the orbital mixing coefficients. So I have those results tabulated here. The chlorine-K edge data, again, has been published previously. And then here are our new numbers for the fluorine-K edge. This is a very small table, but I do want to emphasize that this data took at least 10 years, if not more, to collect. So there's a lot of work that went into each one of these numbers, many, many user proposals, many samples. I don't know how many postdocs, but what you'll notice is that there's not really a significant change in the amount of orbital mixing when you move from the fluoride to the chloride overall. And just in a very simple sense, if we think about the hypothesis that we were talking about before, if the fluoride 2p are lower in energy than the chloride 3p, but we're keeping our metal orbitals at the same energy, then this is an initial sense that the increased energy gap for the fluorides is perhaps being offset by an enhancement in overlap. And that's why we're seeing an enhancement, or essentially the same amount of orbital mixing for both the fluoride and the chloride. So an early indication that overlap is driving covalency for the fluorides, at least more so than it is for the chlorides. And it's sort of, as a sanity check, we went and looked at the cerium system. So this is lanthanide hexafluoride. Here's the fluorine-K edge for that. We see the same sort of peak into the orbital of T2G symmetry, and then a very nicely well-isolated peak associated with the 4F orbitals of T1U and T2U symmetry. Here's some ab initio calculations done by Jochen Autschbach and coworkers. And then here's the data for both the cerium hexafluoride and the cerium hexachloride in this table. Now, what you'll see for the fluorides is that initially this is a very small amount of orbital mixing, and it actually increases when you go from cerium to the actinides. And this is exactly consistent with what I talked about on, I think the second slide of my talk, where I showed that radial distribution function plot, where the 5f orbitals are more extended than the 4f. And so this would be consistent with having greater overlap in the actinides versus the lanthanide system. When we go to the chlorides, though, we actually see the opposite trend. So for cerium hexachloride, we have a fairly large amount of orbital mixing, and then it seems to be dropping when you go to the actinide systems. And so in this case, we could probably describe this trend by thinking not by changes in overlap, but by the changes in the f orbital energies. So when you go from a 5f to a 4f orbital, you're getting a smaller energy gap, and then decreasing your orbital mixing for actinides. And as sort of an additional sanity check, we went into the literature and looked at a relatively recent paper by two of my colleagues here at LBNL, where they looked at optical spectra for several of these hexahalide ions, and are able, using these spectra, to determine the overlap integrals and see, in fact, exactly the same observation that we're predicting here, in that the overlap is dropping as you move across, move from a smaller halide to a heavier halide. And this occurs in both the orbitals of T1U and with T2U symmetry. Now, one thing to point out is that in f orbital systems, it's impossible to separate the orbitals that are sigma bonding from those that are pi bonding. And so it may be the case that the trend is reversed for orbitals that were sigma bonding only, if we could look at those. And that's something that we're going to be interested in looking at more in the future. I also want to emphasize that this is one series of compounds. The trend may be very different if you were to go to something that was lower symmetry, or if you were to look at a different type of ligand. And that's something that we want to explore, I guess, the bounds of this sort of observation more in the future. I'm going to sort of just go through the conclusions quickly, since I'm running out of time. The main thing I want to point out is that using, by varying the ligand and exploring different ligand edges, and by keeping the metal constant, we've been able to probe overlap specifically. In the future, we're trying to go to higher valence systems. So some data from the pentavalent fluoride. Uranium-6 hexafluoride would be great. And also some of the transplutonium fluoride. So we're fortunate to have access here to a small amount of berkelium, which is a very rare isotope. And for acknowledgements, I want to mainly point out Jacob Branson, who did a lot of the fluorine K-edge work. Our colleagues at Los Alamos, Enrique Batista, Dave Clark, Stosh Cosmore, and Ping Yang, and many other theoretical colleagues. And I want to thank the Canadian Light Source and the Department of Energy for funding the Advanced Light Source and SSRL, and for funding our work directly. Thank you.
Great. Thank you so much, Stefan. That was great. I feel like I learned a lot of actinide chemistry in an hour. Are there any questions from anyone else? I guess I have a fairly naive or maybe sample prep question. When you're doing the fluorine work at more like 600 or 700 electron volts, that seems like there's a potential for overlap with a lot more materials, including possibly the N edges of the actinides. Or has that been a concern or a problem that you've run into?
Yes. It's one of those times when you wish nature had designed things differently. It's really unfortunate. So especially for thorium, so the thorium N5 edges straddle the fluorine K-edge peak. So it's basically impossible to do any sort of a quantitative study there. You can't normalize the spectra properly. For uranium, it's challenging, and we have to work very hard to normalize those properly. When you get to neptunium and plutonium, the N5 edges are high enough in energy that you're,
I guess there's a question. Mike, if you have a question, please go ahead.
Hello, Stefan. Thank you for the nice talk. So I'm interested in if you attempted or considered just measuring electron yield of fluorine K-edge as opposed to STXM, and why that is not the method to go with.
So we had tried doing some electron yield measurements many years ago. The main reason we don't do electron yield, well, there are a few reasons. I mean, if you do those measurements right, you can get pretty high quality data. But for our systems, we found that transmission gives much more reliable intensities. And you don't have the sort of surface contamination issues that you might have with electron yield measurements. And especially for actinide systems, it can be particularly difficult to design containment methods when you're trying to do electron yield measurements. It's not impossible, and we are actually doing some of that now on a different beamline at the ALS. But it's taken a lot more work to design sample holders. So, yeah.
Mm-hmm. Thank you. And maybe then could I also ask a little bit as about the general practicalities of handling, these air sensitive, well, radioactive, in some cases, air sensitive samples behind the boron nitride windows. Do you find this, as a facility user, as a way to enable you to transport samples without contamination with air? What are the technical aspects of that? How do you get your sample from your glove box in your lab into the STXM at the national facility?
Right. So yeah, the seal, the barrier to the air in this case is the silicon nitride, which is pretty robust for diffusion of oxygen, I would think. But then you have the epoxy around the edges, and so oxygen could presumably diffuse through the epoxy with time. In general, we find that these samples are able to be in air for at least a few minutes without degrading, but we don't take any chances. So what we will do is package up our samples in Mylar bags in the glove box, multiple layers of Mylar. And then we ship them and try to analyze them as quickly as possible after sample preparation has been done. And with this, we've been able to obtain reproducible data for some pretty air-sensitive compounds. I mean, sericine is among the more air-sensitive compounds I've ever worked with.
Great, thank you for that insight.
Great. Well, we're at the hour, so I'm going to stop the recording. But if anyone else has more questions, that way people can feel free to leave to the next meeting. But if people want to hang out and chat, that's fine. Okay.